Cryptographic hashing and mining, the backbone of blockchain security. Let's start with a scenario you can visualize. Picture 3 people in our story: Alice, Bob, and Eve, who has a habit of snooping where she shouldn't. Alice needs to send Bob an important digital document, maybe a contract or payment confirmation. Her main concern? Making sure it arrives exactly as she sent it, with no tampering along the way. Here's what Alice does. She processes the file through something called a hash function, which generates a unique digital fingerprint. She sends this fingerprint to Bob through a separate secure channel. Think encrypted email. When Bob gets the actual file, he runs it through that same hash function on his end. Now comes the moment of truth. He compares his result with the fingerprint Alice sent. Perfect match? The file is authentic and untouched. But here's where it gets interesting. If Eve managed to intercept that file and changed even a single character, Bob's hash would be completely different from Alice's. That mismatch immediately signals that something went wrong. This exact principle is what blockchain technology uses to guarantee that every transaction and every block stays exactly as it was created. What makes hashing cryptographically secure? Not all hash functions are created equal. For blockchain to work, we need something extraordinarily secure. A proper cryptographic hash function has 3 essential characteristics. First, deterministic behavior. Feed in the same data, get the same hash every single time. No randomness, no variations. Second, collision resistance. This means it's virtually impossible for 2 different pieces of data to produce identical hashes. Imagine trying to find 2 completely different people with matching fingerprints down to the last ridge and whorl. Theoretically conceivable, but practically impossible with strong hash functions. Third, one-way operation. Computing a hash from your original data is straightforward, but trying to reverse engineer the original data from just the hash, that's computationally infeasible, even with supercomputers running for years. These 3 properties make cryptographic hashing perfect for blockchain applications. Bitcoin, for instance, relies on SHA-256. That's Secure Hash Algorithm with a 256-bit output. It's engineered to be fast, bulletproof, and dependable. Every transaction, every block, every digital signature gets verified without ever exposing the underlying information. Hashing keeps everything locked down tight. Real-world context. Let me give you a practical example you might relate to. Imagine downloading a large software update, maybe a new game for your console. The download page provides a hash value for that file. After the download completes, you generate a hash from your downloaded file and compare it to the one provided. Matching hashes confirm the file downloaded correctly, without corruption or tampering. Blockchain networks do this continuously, constantly hashing transactions and blocks to verify everything remains exactly as it should be. There's another benefit worth mentioning: efficiency. Hash outputs are fixed length and much smaller than the original data. This makes storage and comparison incredibly efficient. Rather than embedding complete transaction details in every block header, the network uses hashes as compact representations. It's like summarizing an entire book with a unique code, quick to verify, but impossible to reconstruct the original from the code alone. Understanding mining and proof of work. Now that we understand hashing fundamentals, let's explore mining, the engine that drives blockchain networks like Bitcoin and maintains their security. Mining is how new blocks get added to the blockchain, and it's built around a concept called proof of work. This is where cryptographic hashing truly demonstrates its power, creating a system that's simultaneously secure and decentralized. Here's the simplified version. Miners are individuals or machines competing to append the next block to the blockchain. They gather pending transactions, payments, smart contract executions, and so on, bundle them into a block, and add a special number called a nonce to the block header. The nonce is essentially a random guess. The miner's objective is to keep trying different nonces until they discover one that produces a hash meeting specific criteria, like beginning with a particular number of zeros. This is the proof of work puzzle. It's computationally difficult because you're testing countless nonces. But once you find the correct one, verification by others is trivial. Think of it like a massive combination lock. Miners are testing thousands or millions of combinations trying to open it. Once they find the right combination, everyone else can instantly confirm it works. When a miner discovers a valid nonce, they broadcast their block across the network. Other nodes independently hash that block to verify it meets all the rules. If verification passes, the block joins the blockchain, and the miner receives a cryptocurrency reward, Bitcoin, in this case, for their computational effort. Why this puzzle matters? The proof of work puzzle is crucial for security and trust. Solving it demands substantial computational resources, making cheating expensive and time-consuming. If someone wanted to modify an old block, they'd need to redo the proof of work for that block, plus every subsequent block, all while competing against the rest of the network, continuously adding new blocks. This would require astronomical computing power, more than most attackers could possibly assemble. This difficulty is precisely what makes Bitcoin's blockchain so secure. Mining serves another critical function, consensus. This is the process ensuring everyone in the network agrees on the blockchain's current state. In a decentralized system, there's no central authority declaring this is the official record. Instead, miners compete to propose the next block, and the network accepts the first valid block received. This competitive structure keeps the system fair and prevents any single miner from monopolizing control. Bringing it together. Let's revisit Alice and Bob. Suppose Alice is now a miner working to add a new block containing a transaction where Bob sends cryptocurrency to Charlie. She collects the transactions, adds a nonce, and starts the hashing process. After testing thousands of nonces, she finds one producing a valid hash. She broadcasts this block to the network, where Charlie and other miners verify it by checking the hash. If everything checks out, they add it to their copy of the blockchain, and Alice receives her mining reward. If another miner, let's call him Dave, finds a valid block simultaneously, the network accepts the first one it receives and the other gets discarded. Some systems may give Dave a smaller consolation reward. This consensus mechanism, proof of work, ensures everyone stays synchronized. But it's not without drawbacks. Mining consumes enormous amounts of electricity because miners are perpetually hashing different nonces. You've probably heard stories about Bitcoin mining consuming as much energy as entire countries. This has sparked ongoing debates about environmental impact. Alternative consensus mechanisms. Not every blockchain uses proof of work. Some, like Ethereum, after its 2022 transition, use proof of stake. Instead of competing with raw computing power, validators stake their cryptocurrency to participate in block creation. The more you stake, the higher your probability of being selected to add the next block. Think of it like a raffle. More tickets mean better odds, but there's no energy-intensive hashing involved. Proof of stake is dramatically more energy efficient, though it has trade-offs, like potentially favoring wealthier participants. Bitcoin continues using proof of work because it's battle-tested and exceptionally secure. Other consensus mechanisms exist too. Delegated proof of stake, where users vote for trusted validators, or proof of authority, used in private blockchains. Each approach has strengths and weaknesses, but they all depend on cryptography, often hashing, to ensure security and agreement. Hashing beyond blockchain. Hashing isn't exclusive to blockchain. It's everywhere in technology. When you log into a website, your password gets hashed and stored securely. When you enter your password, the site hashes your input and compares it to the stored hash. Match? You're in. This way, even if hackers compromise the database, they can't read your actual password, because hashing is one way. In blockchain, hashing plays a similar protective role, safeguarding transaction data and ensuring only authorized modifications are accepted. Another powerful application is digital signatures. A digital signature is the blockchain equivalent of signing a check. It uses hashing to prove a transaction came from you and hasn't been modified. When Bob sends Charlie cryptocurrency, he hashes the transaction and signs it with his private key. The network uses his public key to verify the signature's authenticity. Hashing makes this process both fast and secure. Challenges and future directions. Let's address some challenges. Mining's energy consumption remains a significant concern. The difficulty of proof-of-work puzzles adjusts dynamically to maintain consistent block creation, approximately 1 every 10 minutes for Bitcoin. As more miners join, puzzles get harder, demanding more power. This has driven innovations like renewable energy mining operations, but it remains contentious. Another challenge is centralization. While blockchain is designed to be decentralized, mining can concentrate in regions with cheap electricity or among large mining corporations. This raises questions about whether the network remains truly decentralized. Some blockchains are experimenting with ways to democratize mining or validation, lowering hardware requirements or implementing proof of stake. Looking forward, both hashing and mining continue evolving. New hash functions are being developed to withstand quantum computers, which could theoretically break current cryptographic systems. Blockchain networks are exploring hybrid consensus models, combining proof of work and proof of stake to leverage the advantages of both approaches. These developments demonstrate that blockchain is a living technology, continuously adapting to emerging challenges. The big picture. Cryptographic hashing is the foundation of blockchain security. It ensures data integrity by creating unique, tamper-proof fingerprints for transactions and blocks. It links blocks into an immutable chain, making unauthorized changes impossible without breaking network consensus. Mining leverages hashing through proof of work to add new blocks, rewarding miners while securing the network. Together, these processes create a decentralized system where trust emerges from mathematics rather than intermediaries. In Bitcoin, every transaction is hashed to verify integrity. Blocks are chained with hashes, ensuring immutability. Miners compete to solve hashing puzzles, maintaining network security and decentralization. This elegant architecture enables people to transfer value globally without banks or governments, all powered by cryptography.
What's next? We've covered substantial ground today, from hashing fundamentals to mining mechanics and consensus protocols. In future content, we can explore digital signatures, how they prove ownership and authenticate blockchain transactions. If you found hashing fascinating, digital signatures are equally captivating. Quick recap. Hashing transforms data into fixed-length, unique strings, ensuring integrity and linking blocks. Cryptographic hash functions are deterministic, collision-resistant, and one-way, ideal for blockchain. Mining uses proof of work to add blocks, securing the network through computational effort. Consensus mechanisms ensure network-wide agreement on blockchain state, maintaining decentralization and trustworthiness. If you found this exploration valuable, consider sharing it with anyone curious about blockchain technology. Questions and discussions are always welcome in the comments. Thanks for your time and attention. Stay curious, stay secure, and keep exploring the cryptocurrency world.